Welcome back. Let's talk about recursion. I'd like to go through these notes with you. There's about 15 pages, but don't panic. A lot of this is code and we don't need to look at every single line. So what is recursion? Recursion is when a function calls itself. So sometimes this is done by accident, and so you need to be able to recognize it when it happens. And sometimes it's done on purpose. And the reason, briefly stated, the reason we use recursion on purpose is that it can be used to simplify a complex problem. And I'll talk a little bit more about that. All right, so there's something called infinite recursion, or really a better name for this would be uncontrolled recursion. Because there's no such thing as infinite in a computer. Computers are finite machines. And eventually you're going to run out of resources. So specifically when you have recursion, it utilizes memory on the stack. So if you have an uncontrolled recursion, you're going to run out of stack memory, and we call that a stack overflow. All right, so here's what a simple recursion might look like in some code. You have main, and then let's say you call F1. So we come down here to F1, and inside F1 we call F1. So it comes back around into F1 again and calls F1, and back around and calls F1, and back around and calls F1. So I'm kind of moving my pen in a circle here. It's which is an okay thing to do, but keep in mind that we're calling a separate instance of F1. That is, every time F1 is called, memory is allocated on the stack. So it's the same instructions that are running, but different data memory. Okay, so it's the same executable code, you could say, but a separate set of local variables. Now this one here doesn't have any local variables. F1 doesn't have any local variables, but we will be seeing that. So, well, let me take that back. It doesn't have any explicit local variables. Like there's no integer x or anything in here, but there are some implicit data allocations that are made every time you call a function, right? Specifically, the return address for sure is pushed onto the stack. So just calling an empty function like this will result in a stack overflow. Try it if you don't believe me. Okay, so this kind of thing, main calling F1 and F1 calling itself, you would have to be pretty sleepy or drunk or something to notice that to not notice that you did this. So this will cause a uncontrolled recursion, but it's pretty obvious. Now there's something that's a little bit less obvious called mutual recursion, where you have one function calling another function, and then that function could call the first one, and then that first one could call the second one. So that would look like this in code. So here, so main, we start in main, it calls F1, F1 calls F2, we come down here, F2 calls F1, come up here, F1 calls F2, F2 calls F1 calls F2, F2 calls F1, and so we're going back and forth between these two functions, allocating memory on the stack with each one of these guys. So this is two functions. There's two functions involved. It's a little bit harder to see, but in theory, this could happen many functions deep. Like you could have 10 functions that come back and call the first function. Now that it would be very difficult to see that in your code. So that's why you need to be aware of the effects of uncontrolled recursion, the stack overflow. Okay, so when you get a stack overflow, there's a recursion somewhere in your code. All right. So memory is used. I already talked about this. Every time you call a function, you're allocating memory on the stack. All right. So let's just look at some simple recursion examples here. So here's a simple example that has a time complexity of big O of 1. So we're calling this function f, and n is the parameter. N is the local variable that we're passing an argument into. Right? We call that a parameter. Right? A parameter is just a local variable that you can pass a value into. Okay. So n is a parameter. It's also represents the size of the problem here in this thing. So we're just outputting n, and then we're decrementing n, and if n is greater than 0, then we call f again. So this will come back in with n a little bit smaller, print it, decrement it, check it, call it, and it'll keep coming into a new instance of f until n reaches 0, right? That'll terminate. So this conditional right here is used to control the recursion, right? It's used to stop the recursion. So this is a controlled recursion, which you need. You need to have some kind of conditional in a recursive call to stop it. Very much like iteration. Iteration is a loop, right? Just a fancy word for a loop. Just like when you write a for loop, you need to have something that checks when the for loop is going to terminate. Same thing with recursion. You have to have something that checks when the recursion is going to terminate. Okay, so this guy here, it looks very much like a loop, or that is, it behaves like a loop. It keeps coming in and decrementing and in and decrementing and in and decrementing until this conditional is false, and then it terminates. So it behaves like a loop. And we've looked at loops already, and we found that a simple loop has a big O of n. So that's what this has, because it's behaving very much like a loop. For example, if n were 10, this thing would call itself 10 times. And if n were 20, this would call itself 20 times. And if n were 30, this would call itself 30 times. So the amount of work that's done is proportional to the size of n. Okay, so that's what we mean by big O of n. All right, and yeah, and for example, if you called this with 5, it would just count down 5, 4, 3, 2, 1. That's the output. All right, so that's a simple recursive example that behaves very much like a loop, and in fact has the same time complexity as a loop. Here's one that's a little bit more complex, but not much. The only change that I've made here is that when I call f recursively, I divide n by 2. So this is integer division. That is, any fractional value will get truncated, right? So if we call this with 50, then it'll print 50, okay, and then it'll call itself with 50 div 2, so that's 25. So it'll come back into this with 25, and you'll print 25, and then it'll divide 25 by 2, which integer division is 12, so it comes back in with 12, like that. So for 50, we're going to get this many calls. We could even make a table here of n, and then how many number of calls, which we call this the work. The work is just one of the ways we talk about big O, is by thinking about the work. So the number of calls is 1, 2, 3, 4, 5, 6, 7. 7. What if this were 60? What would the number of calls be? I think it'd be about the same, maybe exactly the same. What would be the sequence to it? What would be this output sequence if we did 60? Right. In fact, here I'll do this. So with 50, we did 50, 25, 12, 6, 3, 1, 0, right? What if we did 60? What would we get? We'd get 60, 30, 15, 7, 3, 1, 0. We'd still get 7 calls. What if we did 70? Then we'd get 35, 15, 17, right? I don't know, what was it now? 8? Yeah, 8, 4, 2, 1, 0. It's 1, 2, 3, 4, 5, 6, 7, 8. 8. Now it's going to be 8 for a while. If you try this a couple of times, it's going to be lots of 8s. Now, if you graph this for like, the work versus n. So for 50 and 60, I had 50, right? Then for 70, I had 80. Okay, if I did a bunch more, I'd see a bunch more 8s. And then there's going to be several of those, and several of these, and several of these. If you fit a curve to this, it's log n. So this pattern of these stepping up like this. This is a discrete log. So basically this guy is big O of log n. All right? So what have we looked at? We've looked at just two simple recursive functions here, one that has a time complexity of n and one that has a time complexity of log n. They don't do anything particularly useful. There's no reason that you would use this versus, say, iteration. But there are reasons to use loops, or there are reasons to use recursion instead of iteration. And basically it comes down to, can you see the problem recursively? So I use this term ICU, which comes from Avatar, by the way. But certain problems have a recursive nature to them, all right? And if you can see that recursiveness, this recursive nature, if you can see that, then the code follows quite naturally, right? Now, that's the reason that we use recursion. It's not because the code is going to be more efficient. It might be, but it also might be less efficient. Okay, so there's nothing intrinsically good about recursion from an efficiency point of view. In fact, the call itself adds a little bit of inefficiency because you have to allocate those return addresses, right? There is overhead in the system. Excuse me. There's overhead in the system for managing a recursive call. So, okay, so I just want to state that again. So recursion just by itself, not necessarily a good thing. The real reason we use it is because certain problems have a recursive nature, and if you can see that recursive nature, then it allows you to solve the problem. So here's the classic example is factorial. So factorial of a number is just that number times every number less than that. So 6 factorial is 6 times 5 times 4 times 3 times 2 times 1 is 720. Right? So 2 factorial is just 2 times 1. Well, I guess factorial 0 doesn't count, but I didn't want it to crash on 0, so I made factorial 0, 0. I think maybe you could also make it 1, I think, if you wanted. Base 0 is kind of a funny value for factorial. You can't count it because anything times 0 would give you 0, so you have to do something. But let's just start at 1. So 2 times 1 is 2, and so factorial of 2 is 2, and factorial of 3 is 6 because it's 3 times 2, and factorial of 4 is 24 because it's 4 times 3 times 2, down like that. So if you think about it, and if you can visualize this pattern here, that you only need to look at the last two numbers. So like factorial of 3 is 6, but you can calculate that by doing 3 times 2. That is 3 times the previous factorial. Or like for 6, you can do factorial of 6 is 720, but you can calculate factorial of 6 just by doing 6 times 120, right? Just the factorial of any number is that number times factorial of 1 less than that number, right? 6 times 120 will give you this, or 5 times 24 will give you this, or 4 times 6 will give you that, right? 3 times 2 gives you 6, like that. 6 times 120 gives you 720. That's the ICU. If you can see that each number is related to the previous number in some way, or in this case it's just the previous number, but it could be previous 2 numbers or something. If you can see that, then you can write this general case here. So for any number n, the factorial of that number is just that number times the factorial of the previous number, or factorial of any number is just n times factorial of n minus 1, and then we're done. I mean, we just have these base cases that are defined for 0 and 1, and once again 0 is just a funny case that we need to deal with in the code, but these are the base cases, and then here's the general case, and that's the code. So here's the code. You have the base case for n and the base case for 1. And then you have the general case. Boom, done. So that's the value of recursion, is if you can see the recursive nature of a problem, the code just falls right out of this. So this is actually the hard part, is seeing the recursive nature. But once you have this, writing these lines of code is dead simple, right? They're just base case, boom, boom, recursive case, boom. Okay, so this is factorial. What about the time complexity of this thing? Well, it's going to be big O of n, because it's similar to the first loop that I showed you, where here's the recursive call, and every time you call this recursive call, n is getting smaller by 1. That's very similar to what we did on this first example over here, where here we're decrementing n and then calling, but n's getting smaller by 1 and then we're recursing. That's what we're doing here, is n is getting smaller by 1. So this is going to be big O of n. Okay, here's another classic example of a problem with a recursive nature, the Fibonacci numbers. So Fibonacci sequence is these numbers, right? And it's defined as each number is the sum of the previous two numbers. That's the definition of Fibonacci. The definition itself is recursive. Each number is the sum of the previous two numbers. So this is the 0th Fibonacci number, the first Fibonacci number, the second, the third, the fourth, the fifth, the 6th Fibonacci number, the 7th Fibonacci number. These are indexes, kind of, basically. So the 8th Fibonacci number is 21. It's the sum of the previous two. It's 13 plus 8 gives you 21. And 13 itself is the sum of 8 and 5. Right? So each Fibonacci number is the sum of the previous two, which, or you could say the 8th Fibonacci number is the 7th Fibonacci number plus the 6th Fibonacci number. Or generally speaking, any Fibonacci number n is the sum of the previous Fibonacci number and then the previous Fibonacci number. There's your code. So we have these two base cases, and then we have this general case. And once again, if you can see this, if I see you, if you can see how this is a recursive thing, and come up with this little this way of expressing it here, then the code just falls out of that. Here's the base case for n0, we return 0. Here's n1, we return 1. And then here's the general case for any other n down here. Okay, so what is the time complexity of this thing going to be? Well, we're calling Fibonacci twice. So every call to Fibonacci results in 2 calls to Fibonacci. So you end up doubling every level. Okay, so like if you were calling this with 8, like if you called this from main with the number 8 and you wanted to calculate this 21, what would happen? This would call with 7, and this would call with 6. You'd get 2 more calls. So this would come in here with 7, and then it would come in again with 6. And then the 7 would produce 2 more calls, one with 6 and one with 5. And then this call would come in and result in 2 more calls. So it's going to be doubling every layer. Yeah, we have a little more formal way of analyzing this, but briefly that was it, and I'll talk about it more later. But basically, this is going to be big O of 2 to the n because it doubles. So that's pretty bad. 2 to the n is one of the worst time complexities that we have, almost the worst. So there's quite a difference between this guy and this guy. This guy's not bad. This guy's just big O of n. the factorial one, but this guy's 2 to the n, much worse. So it's not because one's, they're both recursive, but it has nothing to do with the recursion, really, the time complexity. That's just a separate issue. All right. Okay, so Fibonacci has a recursive nature to it, right? Let's look at exponentiation, just some number to some power. Okay, so let's say you wanted to calculate x to the n. Okay, the so-called obvious algorithm is a loop where you multiply some variable times itself. Okay, so I'm trying to calculate x to the n. Here's x, here's n. Start off with 1, because any number to the 0 power is 1. And then you just loop n times, multiplying that answer 1 times x. Right, so if this loop executes 1 time, then it's just going to be x times 1, so you just get x. And if this loop executes twice, you're going to get x first time, and then x times x second time, right? And then if n is 3, this will go 3 times, so you'll get, x, then x squared, and then x cubed. So this is the so-called obvious algorithm, and we use the word obvious in computer science, and in math they use the word obvious all the time, or they use the word clearly. So clearly and obvious just means that nobody knows how to explain it. Okay, so they just say clearly. Okay, so this may not be obvious, but we can't really make it any simpler than that. Okay, this is big O of n, right? Because n is, or I is counting from 0 to n. This loop right here, I is counting from 0 to n, and it executes n times. We've looked at this before. We've looked at loops, iteration, and when they do this kind of counter, an iterator, I is the iterator. Sometimes we use the term counter. Iterator is a better term. Anyway, the iterator I is just going from 0 to n. So the work done, which is just a simple calculation in here, is done n times. So this is big O of n, which isn't terrible, but it's not great. Okay, some genius somewhere figured out that you can do better than big O of n. Some genius, really smart dude figured out that exponentiation has a recursive nature. Okay, so what they figured out, and I didn't put it in a table, I just sort of wrote it out, but any number to the 0th power is 1. And then any number to the 1st power is just that number. So these are the base cases. Then the genius part of it is this stuff here. Somebody figured out that any number to the nth power can be expressed as x squared times that n by 2. Right? Like x to the 16th is x squared to the 8th. Okay, and then also any number to the nth power, if that number n is odd, you just throw another x in there. So n to the x to the 9th power, for example, if n were 9, would be x squared to the 4th. So x squared to the 4th, then throw another x on there. So for odd n, you get this thing, and even n, you get this thing. So some genius, figured this out, and that has a recursive nature because you're dividing by 2, right? You're dividing by well, that's not the recursive part, but well, yeah, that is the recursive part. That you're dividing by 2, or let me say that any number to the n power can be expressed as a previous n, right? X to the n is related to some n halfway back. Okay, so that's the recursive ICU, is that any number to some power is related to some smaller numbers to smaller powers. Okay, so if you can see that, which is not easy to see, but if you can see that, the code is easy. So here's the code, and it just falls out of these recursive cases. So here's the base case. So here's the base case. If n is 0, you return 1 right here. And if n is 1, you return x here. Otherwise, it's either even or it's odd, so you have an if else. And if it's even, you do this x squared n to the n by 2, so x squared is x times x, raised to the power n by 2. So we're calling pow again for this, we're recursing. We're calling pow again for some x to a previous n, specifically n halfway back, right, for even. And then for odd, the same thing, except we throw on another x. Okay, so this ICU, this seeing this recursive nature, that's the hard part, really. And then writing the code is almost a direct translation of this recursive expression, this recursive way of expressing the problem. Okay, so that's the value of recursion, is you know, that certain problems have a recursive nature, and you can see if you can see that recursive nature, then the code follows very directly. All right, let's look at a couple of more algorithms that are recursive. All right, and then that'll be this lecture, and then the next lecture I'll talk about how to analyze these guys. So here's just some classical recursive algorithms. So I have fractal dragon, which I've run in a previous algorithm, and this demo code is posted. You can take a look at it. This is recursive, and it has a 2 to the n, which I've talked about in a previous video. But here's the code, and you can see that it's recursive just by looking at the code. So the name of the function is dragon, and we're calling itself twice, okay, and we're calling it with a smaller value of level. Level is n. So here we call this guy to some depth of recursion, some you know, deep, some you know, how fancy, how detailed we want this picture to be. That's level. And then it calls itself, dragon calls itself twice with 1 level less. So this is similar to Factorial. Okay, and it's gonna have the same time complexity. It's gonna be 2 to the n, because we're doubling with each call. Each call to dragon calls dragon twice more, so it doubles. Every call in here doubles 2 more calls. So we have this 2 to the n. Okay, there's that. And you can run this and watch the other video if you want. Okay, here's another classical problem called the Towers of Hanoi. So this is a little game where the rules are smaller donuts on top. Okay, it has to be tapered up like that with the small guys on top. You can only move 1 at a time. And what you're trying to do is move this entire stack to another peg. Okay, so I've got some executions here. If you were trying to, if n were 1, that if you were trying to move this peg, or one donut from this starting peg to this goal peg, the solution is just move it and you're done. Okay, and if n were 2, that is if you're trying to move 2 donuts from this starting peg to this goal peg, the solution is a little bit more complicated. That is, first you have to move the little guy over to the spare, okay, because you can only move 1 at a time. So you move this little guy over to the spare, and then you move this big guy over to here. Then you can move the little guy back, and you're done. Okay, if you're calling this, if you're doing this for 3, it becomes recursive. So there's a base case for 1 and a base case for 2. Actually, yeah, even this is a little bit recursive, but here's the third. Here's if n is 3. If you're trying to move 3 donuts from this starting peg to this ending peg, right? Trying to move these three from here to here. This is the solution, and it's made up of these previous two solutions. You see the recursive nature? So first we do this. We got to move this little one out of the way, because if we do that, we've broken it into the two problems, the two previous problems. So move this guy over here. Then you've got the previous problem where you're moving two from start peg to the goal peg. It's just that the goal peg becomes this one now. Okay, so in here you're moving these two from here to here, with the goal being here, the starting peg being here, the goal peg being here, and the spare peg being here. So the goal, start, and spare pegs are changing around. But it's a little hard to keep track of it, but it has a recursive nature. So we do this, move the two, then we do this, move the one again, then we do the move the two back, and we've got it. So this isn't super easy to see, but it is recursive, and this is what it looks like in code. We've got the base case for n equals 1, where we just move the disk from the start to the goal. This just prints out what to do, and then you still need a human or a robot to actually move them. So that's the base case for n equals 1. Then this here is the recursive case. So there's really just the one base case. There's the one base case, and then there's move everything above the target disk to the spare peg, then move the target disk, then move everything that you moved previously to the goal peg. All right, and so that is the ICU part, and I'm not saying that that is easy to see. It's not, but when you see that, the code is easy. Let's just look at the code from just a purely time complexity part. We've got Hanoi calling Hanoi twice. Each time it calls Hanoi, the problem gets a little bit, it gets one smaller. So we have Hanoi calling two Hanois, so it's going to double at every level, right? It'll come into Hanoi, call two more Hanois. Those will come into Hanoi and call two more. So we're double, 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 double. So that's another 2 to the n. And I've expressed it with this little table, like if we're trying to move one peg, it's just going to do the base case and done. If you're trying to move two pegs, it's going to call Hanoi twice. Well, first you're going to call Hanoi once, and it's going to call Hanoi twice, and then you'll be done. So it'll be 3 calls to Hanoi. And if you call it for n equals 3, it's going to come in once, 2 more times, and each one of these is going to call 2 more. So you've got 3. This guy results in 2 more calls. This guy results in 2 more calls. There's 3 calls here, 3 calls here, and 1 call here is 7. It's like that. So it's doubling. And what I'm trying to do now mainly is just introduce these algorithms because they're classical recursive algorithms. Now, we need to have a better method to calculate the time complexity, because this is too much to keep in your head. Okay, so yeah, so we'll look at that in another video. All right, anyway, this is Towers of Hanoi. It's recursive. It has a pretty bad time complexity. And yeah, all right. You can run that if you want. That's posted. Okay, here's another classical algorithm getting a little bit more complicated. And we'll look at one more after this. All right, so this is the n queens problem. Presented here is a screenshot of a demo that I have, and this demo is an executable that's posted. You're welcome to run that. So this is showing one solution. So the n queens problem is queens can attack, in the game of chess, queens can attack vertically and horizontally, as well as diagonally. So this, what you're trying to do is place n queens. In this case, n is 8. So you're trying to place 8 queens on a chessboard such that they're all safe. Safety is a big deal now, nowadays. It wasn't when I was growing up, but now it's all about safety, right? So here we have queen, and this queen, the rows and the columns and the diagonals are all clear. And that's true for every queen in this solution here. So this one, the row and the column are clear and the diagonals are clear. Okay, so this is a solution. These 8 queens are all safe. No queen can attack another queen. So the solution is expressed as a stack of numbers where this is every column and the row that you're on. So this is column 0, the queen is on row 1. This is column 1, the queen is on row 6. This is 6. This queen is on row 8. There's the 8. This queen is on row 3. There's the 3. 7, 4, 2, 1, 5. Okay, so the solution is given here in these notes. All of the code, the complete code for n queens is given here. Let's see, so let's just briefly, some of these are helper functions we don't need to go through in detail. Like this print solution, it just prints out this stack. Okay, that's what it does. Cell OK is checking for safety. I probably should have named this function safe or something, like is safe. Is safe would be a better name for this guy. So if the queen is safe, this returns true. Okay, here's the guts of the algorithm. It's called a function called build, which is recursive. So there's the name of the function. Here it is calling itself. Okay, it's calling itself with 1 less each time. So eventually it will stop. That's good. It's controlled. And the added level of complexity in this build algorithm is that the recursive call is in a loop. You see? So P is really row, you know. If I were rewriting this today, which I should, I would use row and is safe and such. Anyway, P is just the row you're on. So it's trying 8 rows, right? P is incrementing until it gets to 8. So it's trying all 8 rows. Yeah, and N represents the column. Okay, so build is called for the first column. P is the row. It tries row 1. Queen is safe on row 1. So it calls for column 2. Okay? Calls for column 2. Column 2 comes into build again. Tries row 1. Queen's not safe there. And so this will increment and call row 2. Queen is not safe there either. So it'll increment for row 3. Queen is safe there. So it'll come back in for column 3. Okay, and you should run this. Download this and say okay to all the warnings that Windows gives you because it's an executable. Run this and play with it. This is posted. Mm. So, so yeah, maybe I'll switch over to my monitor and run this, or at the very least, you should download this. But yeah, eventually, it's going to find a safe position for each queen, and it'll get to the nth column, where n is 8, and the queen will be safe at some row on the 8th column, and that's a solution. So we'll print the solution. So let me start over kind of at a high level and try and talk through this again. So you call cell OK, you call build in main for column 1, comes in here. This guy loops through every row, and when it finds a safe position for the queen, it recurses to the next column. Okay, so you'll come in for column 1, and then that'll go through here looking for safe rows. Right? Eventually it'll find a safe row on column 1, and it'll come back in for column 2, and it'll proceed like that, going deeper and deeper into the recursion until it's at column 8, right? And then it'll back out after it finds the final solution here that for column 8. It'll print that, and then it'll back out and start trying other rows on the previous column until it finds another safe position, and it'll go back into 8. So it's going to try. It's what we call a brute force kind of. It's exhaustive, brute, except it's optimized. So brute force in that it just tries every combination of queens. Well, not exactly. If it tried every single possibility, that would be exhaustive. But it's not really exhaustive. It's optimized. But it doesn't matter for the time complexity. Okay, do you remember when we looked at optimized bubble sort? Optimized bubble sort is still big O of n squared. The optimization doesn't matter. So what we have here is really an optimized queens. It's still going to be, well, what is it going to be? It turns out it's n to the n, which is super bad. Because this guy is called, this build is called n times, right? Because it starts at, in this case, 8, and it's called all the way down to 0. It's called 8 times. And then this inner loop executes 8 times. So it's 8 to the 8th. You might think it's n to the 8th, or it's something else, but it's not. It's n to the n. Okay, it's a little confusing, but that's what it is. And that's if it were exhaustive. It's n to the n. Now this is actually optimized, because if the queen is not safe, right? If this function returns false, the queen is not safe for any given row, it doesn't recurse. It's similar. It's a similar kind of optimization that we used for bubble sort, where bubble sort didn't bother to go all the way to the top. Right, so here we're not bothering to try any more columns if a particular row is not safe. So that's an optimization, but it doesn't matter. So even though this is, let me just say it again, even though this is an optimized, because we're not recursing for row positions that are not safe, even though it's not even though it is optimized, it doesn't really affect the time complexity. Now there's a document that I've where I go through this in much more detail. If you're interested in understanding this deeper, I kind of explain why this is n to the n and why it doesn't why the optimization doesn't matter. But for now, or at the first level of understanding, I just want you to understand a couple of things. I want you to understand the time complexity of bubble sort. I want you to, at the very least, memorize the time complexity of queens. This is an introductory course, so you just want to be exposed to these things. And I want you to keep in mind this idea that the optimization, while that helps, it's not near as important as time complexity. Time complexity trumps everything. I have to use the word trump, but time complexity, I just want to get more hits. That's why I said trump, because I want to get more hits for monetization. But yeah, optimization beats everything else. It's the most important factor. Okay. So this is kind of an introduction to N queens. I'd like you to really run this and just watch it for a while and start it and stop it and just look at what it does and then refer to the code. I'll let you do that on your own. Okay, the last guy we want to run is this maze thing. Once again, I've posted a demo. And let me just kind of go through this and hit the main points. So we're trying to get from this starting position to this ending position. And here is one particular solution being displayed as a stack of numbers. So we're at cell position 1, 1 here, where we start. And then we're at cell position row column. So these coordinates are row column. It's row column. So we're at row 1 column 2. That's this number down in here. Then this is we're at row 1 column 3. Then we're at row 2 column 3, like that. And then we're just going through the 8, 8 down here. Right? Okay, there's another piece of data that's being stored that's not being displayed, and that's the direction. Like here we're moving, let's see, so this is north, this is south, this is west, right? And this is east. So we're at 1, 1 and we're going east. Then we're at 1, 2 and we're going east. Then we're at 1, 3 and we're going south. Then we're going east again. Then we're going south. Then we're going east. Okay, so that's the solution. So let's see, what should we talk about? There's some data representations. We're going to implement this, so we do have to go through this a little bit. I think I'll save that for that other video, but let's look at how this is recursive. So we're calling a function in main called build. All right, and oh, I left out the code. Well, I can't talk about it then. I do need to give you this code though. So we'll talk about that later, but it is recursive and it's very much similar to the Queen's algorithm. And we'll talk about that later. You could run this demo if you want and look at that. Yeah. All right, so just to summarize what the main lessons on this thing are there's this thing called recursion. We went through the basic definition. We looked at a couple of simple examples, but the main value in recursion is that if you can see how something is recursive, if you can see the recursive nature of something, then the code tends to be, I don't want to say easy, but it tends to follow directly from the recursive expression of the problem. And we looked at one of my favorites, this efficient explanation. Some genius figured out this pattern, and then you get this. And there's some other classic ones, Fractal Dragon, Hanoi. You can, yeah. All right. I hope that was helpful. We'll see you later.